So it's been a couple of weeks, I think, since we've been in face-to-face with me and you here at the same time, which is like bizarre, but that's kind of where we're at. We're going to do kind of go through in-class examples, as many as we can do today. I'm going to call on random people to kind of help talk through these things. My suggestion to you is that while we're doing this, like, take some notes, like write down some of your own work, have your calculator out to follow along. Like, I know it's been a little while since we've been here in person and gotten any kind of like direct instruction from me. That's what we're trying to do right now, is to kind of get caught up on things. So I highly encourage you to like really kind of engage with this time, and so you're not stuck trying to do it on your own with no advice and no input, no like, hey, this is how we kind of do a problem that looks like this. And like, okay, let's walk through this together and talk about what these things mean and how to do that. You know, like, because I am going to ask you in the not too distant future to be able to do this on your own, right? Okay. The first random draw name is Isaac, so we got that. So we're looking in 12.1, example 1, part A. So we read, it says, suppose you have two fair die, or dice, meaning all sides are equally likely to face up when the dice is rolled. The first die is four-sided. It has the numbers 2, 4, 6, 8. And the second die is three-sided. The numbers on it are 1, 3, 3. Part A says, let event X be the number that appears on the first die. Write a probability distribution for the variable X. So what should a probability distribution look like? Okay, so it should be a list of all the possible outcomes and the probability that each outcome occurs. So here our situation is the number that appears on the first die. What are the outcomes that can appear on the first die? What can we roll?
2, 4, 6.
Great. So our probability distribution really just needs to be those four probabilities, right?
And then it's 0.25 for awful.
Great. How did you get that?
It's all equal score.
Great. They're all equally likely. There's four outcomes, so just 1 out of 4 for each of them. You could write that as 1/4. You can write it as 0.25. Either one is fine. To know our probability distribution is correct, what does it need to add up to be? 1 or 100%. Exactly, yeah. You could write them as 25% also. That would be fine as well. Everybody okay with how we did that first one? Easy question, right? Do we have to know what probability distribution meant? Sure, but after I described what it meant, pretty easy. Let's see, who's going to be next? Luke, you're next.
So we were doing just like how we did the last time. It would be like P1 equals 0.33.
Okay, I'm going to write as 1/3 so we don't do any rounding.
Okay, no rounding. So, and just do that for the rest of them. 3 is equal to 1/3.
Is it equal to 1/3 though? Because what are the outcomes that can we get from the second die?
3.
1 and 3, right?
Yeah.
Okay, so what's the probability of getting a 3 then? How many times can you get how many different ways can you get a 3?
Twice.
So it's like 2 times
Oh, okay.
1/3 or 2/3. right? Because the 3 is just one outcome. It doesn't matter that it's on two sides of the die. That's just one outcome for our independent variable, or our random variable. Does that make sense? So it's like 1/3 chance you get a 1, 2/3 chance you get a 3, because there's 2 ways to get a 3. They're all equally likely. All right. Questions so far? Is this going okay? No big deal so far? Again, talking through what's going on, I think, again, super helpful. Diego, you're up next.
Okay. So we're gonna write P and then every single number.
Yep. So we want a probability distribution. The 2 die are rolled together and then added up.
Okay, so 2.
How are you going to get a 2?
Oh, never mind. 3.
3 is your smallest number you can get. 1 plus 2. Okay, what's the next smallest number we can get?
4. No.
Nope, I don't think you can get a 4.
5.
5. Again, 1 plus 4 or 2 plus 3. What else can we get?
7.
7, good. Again, 1 and 6 or 3 and 4.
9.
9, good. That's 6 and 3 or 8 and 1. And there's one more.
11.
Okay. Now we have to calculate the probabilities for these.
So the first one, it's
I need to get a 2 on the first die and a 1 on the second die, right? It's the only way to do it. I thought of 0.25 as 1/4, so the arithmetic would be easy. Decimals were going to be silly at this point. Okay. And now, how many different ways how can we get a 5?
2 ways. But 3, 2, and 1 and 4.
Okay, so if I do 1 and 4, that's going to be 1/12, right? And then 3 and 2 would be 2/12s, right? So together we have 3/12s. Now you could reduce that fraction, but you don't have to. I would probably not, because it'll make common denominators will make it easier to check to make sure our probability distribution is correct at the end. Okay. How about 7?
So 1/12 again with the 1 and 6
Okay, for 1 and 6, good.
plus 4 and 3, so that's 2 and 12.
2/12s again. I guess we could write this underneath that, huh? And then this was 1 and 6, and this was 3 and 4. Okay. How about 9?
1 and 8 for 1/12.
Okay.
And plus 2 12s is 3 and 6.
Okay. And then 11.
2 12s.
2/12s only. Is the only way to get that is 3 and 6.
Okay.
And if we add those together, we do get 12/12s. So at that point, we're pretty satisfied, right? How do you guys feel so far. Was that one okay? Alternatively, you could have drawn like a tree diagram to make sure you counted all the outcomes. I don't think that's really necessary for this. You just had to use look at the different ways you can get there and use what we had calculated previously, which I think is enough. Is everybody okay with how we got like the 1/12 and 2/12 in all those places? Okay. Again, if I'm doing something you don't understand, stop me. Or if you have a question, stop me. Or if you just need to hear it again, stop me. Elise, you're next. So the probability that A is greater than 5 would be the probability, or greater than or equal to B to 5 would be probability of 5,
and 5, sorry.
plus 7, plus 9, plus 11, right? So we have 3/12 plus 3/12 plus 3/12 plus 2/12, which is 11/12. Or what else? What's the other way you could have done this?
Just 12 times 1.
Or the probability that P of A is strictly less than 5, which would be just P of 3. Now here, because we had the entire probability distribution, it was not a hassle either way of doing it. So I didn't make a big deal about not doing the complement here. But if you had to if you didn't have the whole probability distribution already, I would much rather do the complement than have to, calculate those 4 probabilities. Does that feel okay? We feel clear as to what we need for a probability distribution? All right. Let's look at this next one. So here we're given a probability distribution, and we're asked to, there it is, to find the value for K. And Christian, this is going to be yours.
I don't really know how to do this one.
So the key is that it's a probability distribution.
Okay.
So what do we know about a probability distribution? All of the probabilities have to add to 1. So we're just going to write down that. And what can I do from there?
Want to square root everything?
I wouldn't want to do that yet.
Divide by, or you add up all the similar terms, right?
Yes, there you go. So if I add the k squareds together, I have 8k squareds. If I add the regular k's together, I have 2 of those. And what does this look like now? Yeah, but it has a name, right?
Yeah.
It starts with a Q,
Quadratic.
a quadratic equation. To solve a quadratic equation, what do we need to do? What does it have to equal?
That's, you want to factor, right? Or
Correct, but before I can do something like that, it has to equal
1.
0. So we'd want to move the 1 over to the other side, so subtract 1 from both sides. And now, to solve this quadratic, which is what we need to do to find our value for k,
Yeah.
we could either factor Now, does factoring work every single time?
No.
No, right? Some things are just not factorable. What else can we do?
The quadratic equation.
The quadratic formula. That's probably the route I would take, in particular, since I see the leading coefficient is not 1.
Yeah.
Factoring, it's going to be kind of a hassle. It wouldn't be terrible because, you know, the other number is -1, so just I know it's a plus or minus 1 for the second part of my factor, but like
Yeah.
the rest of it's, you know. So if we did this as a quadratic formula, that's -b, again, where these are a, b, and c, plus or minus b squared minus 4ac all over 2 times a. So 4 minus a -32 is 36. The square root of 36 is 6. So if I do the negative, -2 minus 6 is -8 over 16, or -1/2. And then -2 plus 6 is 4 over 16, which is 1/4. How do I know which one that I want?
You'd have to plug it back in, right?
Nope, I can do it probably without plugging it back in.
I don't know.
So what else? Remember, K is a probability, right?
Yeah.
So what numbers does K have to be between?
It has to be 0 and 1.
Between 0 and 1.
So it can't be the negative.
Yeah, so I can discard that one immediately. And okay, that's the one I must want. Now to check it, you could actually do 1/4 plus 3 times 1/4 squared plus 1/4 plus 4 times 1/4 squared plus 1/4 and make sure it equals 1. It does. So I'm not even gonna,
Okay.
but the calculator could do that pretty easily for you. But that's the idea, right? So
Yeah.
again, probability distribution, add up all the probabilities has to equal 1. And there's just we have an equation with one variable. We just use the appropriate method. In this case, it was solving a quadratic. And then maybe we have to think about, like, okay, of the answers that we got, which ones are appropriate? If they're both positive numbers that are both between 0 and 1, then it could be okay, right? Does that feel okay on how to do something like that?
Yeah.
Okay. Let's look at the next one here. Let's see who's up next. Aiden, who's gone. Go to the next person. Megan, you're next. I know you're excited. So this is very similar to the previous problem, right? What's making this a little bit harder, though? It's not that it's that you have two variables, right? So I would start the same way. But can I solve an equation that has two variables in it with just one equation? No. So that's why they also tell us that, in addition, this is true. So I'm going to use that to create a second equation. It'll form like a system of two equations that I'm then use to solve for A and B. So what would I write for 4 times P of Q less than or equal to 1 equals 5 times P of Q equals 3? I'm going to turn that into an equation of A and B's.
So like 4 times P of 0 and 1.
Okay.
5 times P of 3.
That sounds fine. So what is P of 0?
4A.
Okay, and what's P of 1?
A.
So that's going to be 20A then, right? 4A plus 1A is 5A, and then times 4 is 20. And then what was P of 3? 2B, so 5 times that is 10B. Or really, I'm just going to write that as 2A is equal to B. Make a substitution.
4A is 3.
So I have 6A plus 2 times 2A, all equals 1. And hopefully there it doesn't take too much effort to see that A has to be 1/10. You see that? And then B is 2/10. And again, you could reduce 2/10 to 1/5, but like, nobody needs you to do that. Or you could write as 0.1 and 0.2, or you could write as 10% and 20%. Any of those is fine. Was that okay? So again, same idea as the previous problem. There's just like the algebra was a little different, right? But the setup was kind of the exact same thing. Lexi, you're next. Do you remember what this capital E means when we write E of a random variable? E stands for expectation, or the expected value. You could use those two terms interchangeably. So if we go back to example 1, it says A, so this is part C was the one with A, and it wants the expected value. So that's going to be the outcome times the probability of that outcome, and for all outcomes.
And you just.
And then just add them up. So 3 times 1 12, plus 5 times 3 12s, plus 7 times 3 12s, plus 9 times 3 12s, plus 11 times 2 12s.
So it's the outcome times probability for all,
Yep,
like whatever you're trying to.
for the entire probability distribution. Yes. So what did we say? 3 times 1 12 plus 5 times 3 12s plus 7 times 3 12s plus 9 times 3 12s plus 11 times 2 12s. And when we do that, we get 22 thirds, which is about 7.3, or I'll just write it that way. Hard equal sign, we'll use that little vernaculum or whatever. And again, that fraction, multiplication, and addition, how are we doing that? Just typing that junk into your calculator, right? Nobody's doing that stuff by hand. But pretty easy, right? Essentially, all this is like a weighted average, right? All right. So again, the capital E there stands for expectation or expected value. Matthew, you're next here for part B. So again, this says that for example 2, find the expectation of Z. So if I go back to example 2, we have this probability distribution. What's the problem here with how this is given, though? We don't have the probabilities for these guys yet, right? So what are we going to do? We're going to take our value for k and plug it back in to get the probabilities for these. So we're going to use that k we just found. And I'll do that quickly here in my head. And I'm going to rewrite these guys as just 4/16 to just make it easier to check that we did that correctly. To make sure that I've done that correctly, how do I check that real quick? Those should add to give us 1. And they do, right? Okay, now that I have that, now to calculate the expectation, I'm going to do the outcome times the probability plus the outcome times the probability, outcome times probability, and just keep on doing that for all possible outcomes. And that's the gist of it, right? So whenever I see that expectation, that's just outcome times probability plus outcome times probability, outcome times probability, plus outcome times probability, plus outcome times probability. So 39/16, or if you wanted to as a decimal, that's about 2.44 rounded to 3 sig figs. Again, not too bad, right? You had to remember how to do that expectation, but the actual process of what that calculation is pretty simple, right? There's no nasty algebra involved in that. You just had to remember what things meant. Zach, you're up next here for 4C. So it wants the expectation of Q from example 3. Yup. So if A was 1/10 and B is 2/10. So we go ahead and plug those values back in. And then tell me what I'd write here. Let's help you with the first one then. So I'm going to do the outcome times the probability for that outcome. So the first one would be 0 times 4/10. Good. 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 Yeah, and you plug into your calculator, it equals whatever. I'll handle that part for everybody. But that's it. That's the whole gist of it, right? Now, again, not a super duper big deal. You just have to kind of know what the symbol means, and the actual calculation that you have to do is really straightforward. All right, let's see. Who do we got next? We're getting right down to it. There's only a couple of people left here, huh? Lucas, you're in the list now. Don't worry. I fixed that from last time. It says you buy $10 worth of raffle tickets. You place them into various drawings worth $20, $50, $200, $500, and $1,000. Let T be the random variable which represents the amount of money won on each ticket. T has the probability distribution given in the table below. Determine the probability T equals 0. What do we know about a probability distribution? Yep. So we'll just say P of 0, which we don't know, plus 0.15, plus 0.055, plus 0.011, plus 0.0025, plus 0.0006 has to equal 1. And now we just do some algebra 1 algebra, and we get that that probability is 0.7809. Feel okay there? Just some like algebra 1 algebra there. Okay. Do I have anybody left in here? Oh, Gavin, who's absent. Oh, reloading. Lexi, you're next. Expectation.
I know this one.
Yeah. Tell me what to write.
Wait, so I do the like bottom line times the, or no, the probabilities, right? The probability distribution.
You just tell me what to write, and I'll tell you if it's right or wrong.
No, I don't
Okay.
really know what to write.
That's okay.
0.15 times, or wait, 0 times 0.15? Oh, that. Okay, yeah, that's what I was gonna do. 7 times. Okay, and then plus 20 times 0.15 plus 50 times
Mm-hmm.
0.055 plus 200 times 0.011 plus 500 times 0.0025 plus 1,000 times 0.0006.
Good. That's correct. Now, if you had left that first piece of the sum off, would that have been okay still? If I didn't include that piece. Well, what is that? What is 0 times 0.708?
0,
So it wouldn't have mattered if you had skipped it. So not a bad, reasonably fair drawing, right? Since basically you're betting $10 and your expected return is $9.80. If you're ever making your own lottery, what do you definitely don't want to have happen? You definitely don't want the expected value to be greater than the ticket price. That's how you're going to go bankrupt running any kind of gambling operation, is if the expected value is more than the cost to play. That's how you lose all, that's how you bankrupt your casino. Even there at 0.98, it feels like a pretty slim margin to be making any money on this, but maybe it's just for charity or something. If you wanted to know which one of these bets is the best bet, how would you know? Like, you have these 5 different tickets you could buy, or drawings you could enter, right? The $20 drawing, the 50, the 200, the 500, or the 1,000. If you multiply the winnings times the probability, it gives you the expected value of one ticket in that drawing, and whichever one has the highest expected value would be the one that's like, oh, that's the drawing I should play, because you have the, like the best return on, investment or whatever. Ideally, if you were a smart gambling operation, they'd all have the exact same return. Okay, one more question here. Let's see who's next. I just want to talk about gambling because it seems like from some of the side conversations I hear that some of us are interested in gambling. Diego, you're the last one. How much would you expect to win or lose when you buy $10 worth of raffle tickets?
Wait. Do I use the expected
Mm-hmm.
minus the, yeah, do I just do 10 minus that? Okay.
So here's the way you'd answer this. You would expect to lose 20 cents because 10 minus E of t. Oops, I'm sorry. So the expected is the amount you'd be expecting to win minus the cost to play. So that's kind of the idea there. Does that make sense and kind of how to interpret that?
Yeah.
And again, as we spoke, if you're doing any kind of gambling, the expected amount you're winning should never be more than the cost to play, or else somebody's casino's going out of business. Because it's just keep buying them tickets, keep on playing. Because I know over the long run, I'm making money out of this, no matter how bad I'm doing in the short run. All right. On to section 2. So here we started using the binomial distribution on your calculator. So you probably want your calculator out and queued up. Luke, you're going to be the first one to go here. Isn't that exciting? Okay, let me do this for a second and see. Okay. No. Okay. Didn't think it would let me do that. All right. So it says there are 12 students in a class. There are exactly 5 girls and 7 boys. You want to determine the probability of selecting 3 boys in a row with replacement if you were to select only 3 students at random. Let X be the event that you selected a boy and show that X satisfies the conditions to be a binomial distribution.
Where do you go with binomial distribution?
Well, this is a definition question. It's not going to be any kind of a calculation. So there's 4 things that you need to confirm to show something's a binomial distribution. So when you think about binomial distribution, you want to think about flipping a coin. Okay? So you need a fixed number of trials. Do we have a fixed number of trials here?
Yes.
Yes. Why?
Because
What part of the story tells you that there's a fixed number of trials?
you can't articulate it.
That's okay. I'm going to give you time.
Because there's 5 girls and 7 boys. And select all 3 students.
So it's because you're doing 3 draws. 1, 2, 3. Fixed number of trials. Each trial has only 2 outcomes. If you think about a coin flip, it's heads or tails. In this, the 2 outcomes are boy or girl.
Yeah.
It's okay. The second, or the third thing is that the probability of success needs to be constant. So a success in this case is considered of getting a boy. What's that probability?
It would be 7 out of 12.
Good. And how do you know that that's constant? There's a phrase in here that's telling you it's constant?
With replacement.
Yes, good. If there's no replacement, the probability of getting a boy each time is going to change, right? And then you need independence. And again, how do we know that this is independent? It's because of the replacement. Thinking about, again, if you think about a coin flip, you flip coin twice, the first flip has nothing to do with the outcome of the second flip, right? They have no effect on each other. It's independent. So again, flipping a coin is your classic example of a binomial experiment. But those are the four things you need to show. And again, by show, oftentimes it's just going to be like you state and the reason is given to you in the explanation, right? There's not really anything to calculate here. All right. Let's see, who's next? Zach. Yep, we reloaded. So here it asks you to write the binomial distribution for the situation above in the form this. So your job is going to be to just fill in the value, the number for P, for N, and then P. N is the number of trials. Okay. So read the last line in the problem where it says, if you were to select only 3 students at random, so the number of trials is 3 because you're drawing 3 things. The P is the probability of success. So a success in this case would be the probability of getting a boy. Mm-hmm.
I'm not sure.
How many boys are there in the class?
7 boys, just 5 girls.
And out of how many total people in the class?
12.
Yeah. So 7 out of 12, right? That's your odds of getting a boy. Done. That's all you need to do. So just filling in the N and the P into the form that it's given.
So N is trials.
N is the number of trials. P is the probability of success.
Okay.
Yep. Again, not difficult, but you have to know what the stuff means, right? All right. Aiden's not here. Gavin's not here. Matthew's in the bathroom. This is Lucas, you're next. All right. It says find the probability, or I'm sorry, find the exact value of picking exactly 2 boys in the 3 trials. So you want really this, right? So we're going to use our, we can do this by hand. So if we go back and there's a formula. Let me open that up real quick and pull the formula. I picked the wrong thing. Where's my formula? There's our formula right there.
Yeah.
Okay, so this is our formula. So it's going to be n choose r times p to the r times 1 minus p to the n minus r. So n in this case is 3. R in this case is 2. P was 7/12. And then 1 minus P is 5/12. And then n minus R is 1. So that's what we're going to be calculating. The formula for 3 choose 2 is this. So n factorial over r factorial times n minus r factorial. So remember what factorial means, the exclamation point? 3 factorial just means 3 times 2 times 1. 2 factorial just means like 2 times 1. 3 minus 2 is 1, and 1 factorial is just 1. So if we multiply this across, I have 2 times 2 times 12 to the third. And on top I have 3 times 2, that's 6, times 5 is 30, times 7 squared. And now I'll go to my calculator and grind that the rest of the way out. So 1470 over 3456. Or that simplifies down to 245 over 576. Yes, you may. Alternatively, you can do that same calculation on your calculator. So if you have your calculator with you and you want to follow along, that would be maybe a good idea. So if you press second and then the vars button, vars is right underneath the down arrow. That opens the distributions menu. And what we want is to scroll down till we find the binomial PDF, stands for probability density function. So for our experiment, we have 3 trials. The probability is 7/12, and the X value, the number of successes in this case, is 2. So I'll just fill that into my table, and I press enter. That's my number, and if I press math fraction, it'll give me the value. So again, if you have a strict equals, we're going to be using PDF. If it's an inequality, we're going to use CDF. And that'll, whoever's doing the next one will get to do that.
I think Matthew should be here.
Oh, that's a good idea. Matthew, why don't you do the next one? Your name came up while you're in the bathroom. You can thank your friend.
Not too sure how to do this one.
Okay. Oops. So to use your graphing calculator, this symbol has to be a or equal to inequality. And that's okay here because what we have is a discrete distribution. You can't get like 1.9 successes here because, well, it's just the number of boys that you're drawing. So less than 2 has to be the same thing as less than or equal to 1. Right? Because less than 2 means you either got 1 boy or 0 boys. Less than or equal to 1 means you got 1 boy or 0 boys. Feel okay? Now that it's written as a less than or equal to inequality, we can use our calculator to do this. So we'll do the same thing. We'll go to second vars. We'll pick binomial CDF. Since it's an inequality, we need to use the CDF. Yeah. So again, this experiment had 3 trials. Probability was 7 out of 12. And we want 1 as our x value because it was less than or equal to 1. And that gives me 0.76 yada yada yada. And if it wanted an exact value, if you do math and then fraction, it'll give it to you as a fraction. 325 out of 864. Or you could give it rounded to 3 decimal places. Does that feel okay? Now, if you wanted to do this another way, what else could you have done? You could just do P of 1 plus P of 0. And you could do the PDF for each of these and like add those up, right? That would be okay. Let's see. Who's next now? Isaac. Find the probability that x is less than or equal to 2 using your GDC. What am I doing? Good. So I'll use binomial CDF. That's correct, since it's an inequality. Yes. And if I do math, frac, so 1385 out of 1728. But this stuff should be, once you know how to use the calculator and get these things set up, there's no real work to do here, right? The work is understanding what the question is asking for and knowing how to set it up on your calculator. But the calculator is going to do all the calculation for you. Like, let it do it. It's really good at it. And as we saw with Lucas's problem here, when they asked for the exact value, like that's a hassle to grind out by hand. And that's just for one outcome, not like 2 or 3 or 4 or 5, right? Okay. Let's see, who's next? Get those calculators ready. Megan, you're next. So let B be the binomial distribution, B of 8, 2/3. Find the following probabilities. So for probability B equals 5, what am I going to do?
Do you do the bars thing or no?
Mm-hmm.
Okay.
Yep. Which one of the two do I pick?
PDF?
Correct, because it's an equals. Number of trials is? Very good. And the P is
2/3.
good. And the X is
5.
great. And you're done. So 0.273. So the way I remember it is the C in CDF is cumulative distribution. So that means you're going to be adding stuff up. That's what we do when we calculate the probability with a inequality, is you have to add stuff up. It's an accumulation. Christian, good timing, asking questions, because you're next.
So we want to go to would it be CDF this time?
Yes, sir, because it's an inequality. Oops, but not the Poisson. I want the binomial. Okay. Trials is
8.
good,
And the P is 2/3.
correct?
And the X value is 3.
Yes. So 0.07879. Elise, this is the tricky one.
CDF?
Yes, but we're not going to our calculator first. There's 2 things wrong with the way this is written. That symbol needs to be a less than or equal to. So how can we change that into a less than symbol? We do the complement, right? So we're going to do 1 minus the probability that B is not greater than 6. What does not greater than 6 mean? What are the numbers that are not greater than 6?
Anything under 6?
Okay. So, and 6. Right? If you're not greater than 6, you could be 6 still, right? 6 is not greater than 6, it's equal. So if you're negating a strict inequality, it gets you the or equal to version. Does that look okay so far? Okay. Now, can we type this into our calculator? Yes. So don't forget to do the 1 minus first. And then what are we using?
CDF.
Good. So binomial CDF. And what are we putting in?
8 trials, P's 2, 3, X values of 6.
Great. So 0.195. this thing that we did right here, almost certainly you'll have to do that again, right? That's a very common trick to get it the way you need it to be, okay? And that works for any probability distribution, right? Just not binomials, because we talk about normal distributions here in the next section, I think. All right. Yeah, he wrote these materials back in the day. I know. Zach, it's yours. So new scenario, let event H be Mr. Chun checks in homework. The probability that Mr. Chun will check in homework on a given day is 0.85. Assuming that each day is independent, write the following events in correct notation, and then use your GDC to solve for the indicated probability. Okay. So Mr. Part A says Mr. Chun checks in homework 4 days in a row.
So that'd be like 0.85
No. So this is a binomial experiment. So we'd want to start by writing this.
Hold it in.
Yeah, so if I need 4 in a row, n is 4, right? So I'm going to do like binomial PDF, 4 trials, 0.85, x equals 4. Again, we're PDFing because it's an equal sign. So 0.522. Megan. For 3 consecutive days, Mr. Chun checks in homework exactly once. Great. PDF or CDF? Good. Number of trials is? Good. 0.85 stays the same, and the x is? Great. Tell me what you get when you type in your calculator. I see you already typing. Oh, Megan. How about 0.0574? I have extras up here if you'd like to borrow one. You can plug yours into the charger there on the power strip and get some juice in it before you go. No problem. All right, let's see who's next. Elise. In a 5-day week, Mr. Chun checks in homework exactly 3 times.
So x equals 3.
Good. PDF or CDF? Good, because it says exactly. The n is?
45.
Good. And then 0.85 is still a probability, and the x is? Good. When you type that in, tell us what you get.
agree.
Fantastic. We feeling any better about this stuff yet here, folks? Yeah. Luke, good thing you said yes, because you're the next person that came up. It's almost like the computer forced you to do it.
Is it X equals 4?
No.
Oh, it's not. At least. So it would be greater than 4. And then it's a CDF. Because it says at least.
Well, we have to do something with that before we can do the CDF. Because look at the way the inequality is facing. So to use the CDF, it has to be less than or equal to, right? So we do a complement to it. That's like that, right? What does not greater than or equal to 4 mean? No, it means strictly less than. Right? If you're not 4 or bigger, you have to be less than 4. Now, for this experiment, what outcomes are less than 4? 3, 2, 1, and 0, right? So I could also write this as less than or equal to 3. Because 3, 2, 1, and 0 is also less than or equal to 3. And now we go to our calculator. So this is a CDF problem. As you had said before, the number of trials is?
It was at least 4 days.
Well,
So there's 5
it's
days.
5-day week,
Yeah,
yep.
5 day week.
And then,
0.85 score.
nope.
Oh, X is
3.
yes.
So if you type that bad mama jamma in,
It would be 0.16.
but you have to do 1 minus that number,
Oh.
right? So it's 0.83735 or whatever, because you forgot the 1 minus.
0.83.
Yeah, because this is like, that number is 0.165. Those are tough ones, right? Let's see. We just got a couple more minutes. That's okay. Aiden's not here. Matthew, you got a hard one here. In 2 consecutive 5-day weeks, Mr. Chun checks in homework at least 4 days each week.
Will help.
Okay. So let's do 5-day week, checks in homework at least 4 days. So read part D. That part sounds like the same problem, right? And if they're happening one right after another, they have to be like a product, right? We know what this number is. So we're just going to steal that. That's it. But that's the trick, right? If we're doing 2 consecutive 5-day weeks, we check homework at least 4 times, well, that's going to be the same as 1 5-day week and then another 5-day week afterwards where the same thing happens. So you just multiply the 2 together. Just like if I want 2 heads in a row, I do 1/2 times 1/2 if I'm flipping a coin. Same idea. Okay. So it says find the expected number, i.e. the mean, and then the variance, and then the standard deviation for each of the following distributions. Okay. Do you remember the formulas to do this? Probably not. Let's write them down real quick. So those are the formulas we'll need for that. Let's see who's going to get to do this one then. Christian.
Not doing A,
Yes, sir.
so it would be E of x equals 8 times 0.6,
Fantastic.
which is
0.48. Or I'm sorry, 4.8. Too many decimals. Okay.
then
What's Q in this formula?
1 minus P.
Good.
So it's 1 minus 0.6.
Yep, so 0.4.
That would be 1.92.
Great.
Then let's say the square root of
Mm-hmm.
P times Q.
Yep.
So then it's just the square root of all that, which is
1.39. Yeah, very good.
Can you define Q?
Q is 1 minus P. And then that's for X
Oh,
binomial distribution NP. Right. So for part B, what's N?
oh, the 11.
Good. What's P?
0.3.
And what's Q?
1 minus 0.5.
Or 0.42? Yes. That sounds great. Let's actually skip these next two. It's like the same thing over and over again. Everybody's okay with that? Just plugging stuff into a formula, just so we can finish this here. So this one says that you determine your chances of winning a game of rock, paper, scissors is 35%. Decide to play 6 games of rock, paper, scissors with your friend. Suppose R is the number of games you win. Find probability that R is equal to 2. Does this sound like a binomial distribution to you? Sure should, right? Because there's either win or lose, right? Are we going to be using a CDF or PDF?
Yeah.
Good. What's the number of trials?
6.
Okay. What's the probability of success?
1.35.
And what's the N? the x, excuse me, 2. So if I type that in, I get 0.328. So that says write the probability distribution here. What are the possible values or outcomes for R? R is the number of times you win. Close. 0 through 6, right? You can win no games. So we need P of 0, P of 1, P of 2. And how am I going to calculate each of these? I'm going to use a binomial PDF, right? So I'm just using the same binomial PDF I just used. So like 0.0754, 0.243, 0.328, notice that. I'm going to skip writing the rest of these out. One thing worth noting is because you're rounding, is this going to equal exactly 1 if you round these numbers? It might not. You might be off by, like 100 or 1,000th, one way or the other. It's not the end of the world. Don't get bent out of shape there. Find and interpret the meaning for R, or the mean for R. What is the mean of R? The expected number of wins when you play 6 games against your friend. So to do that, you're just doing like 0 times 0.754 plus 1 times 0.243, 2 times 0.328 plus yada, yada, yada. Right?
It's not the number of trials times the probability.
I'm not sure if you'd get I think you probably get the same number. I'm not sure. That's not the notes that I had written down as to how I did it. The last one, standard deviation. Just this, right? Okay. Have a good day, folks. Hopefully you feel a bit better about what we've been doing.
So